what I'd like to do here is use our same data set of 5 commute times, 72, 61, 72, 85, 90, 92, and use the prediction h equals 80. Remember, 80 is the mean of all the y's, okay? Which means it is the prediction that minimizes the average of the squared losses. So 80, which is the mean of the y's, minimizes the average squared loss. Okay? And so what I'd like to do is just draw out what the squared losses are for each data point, and then also what the absolute losses are. Okay? So the absolute ones are easier to do because all we have to do is square those. What's the absolute loss for this data point? 8. What's this one? 10. This one, 19. This one, 5. And this one, 12. Okay? And I know it's going to be hard to differentiate the purple and red with the projector. So what I did last class is I underlined them, the absolute ones. Okay? What are the squared losses? Well, it's just the absolute ones squared. Okay? And here's the big idea. And again, just to clarify, what I've written here are the absolute losses. And what I've written here are my squared losses. Here's the big idea. The prediction of 80, it's the one that minimizes the average of the 5 red numbers. That is the 5 squared losses. Do we agree? But that doesn't mean it's the same number that minimizes the average of the 5 purple numbers. Okay? It could be, but it could not. Like, it could also not be. I don't know. All right? And so that's what we're starting to get at. But not necessarily the average absolute loss. Okay? It's hard to tell from this picture if it does or doesn't. But my point is that 80 is the optimal prediction for squared loss because it has the smallest average squared loss. But if what we think is a good prediction is one with small average absolute loss, well then 80 may or may not be the best prediction. Okay? And so to illustrate that point further, I want to draw a number line. Okay? And this is going to get a little messy, but bear with me. Let's take a look at the prediction h equals 80. What I'd like to do is first find all 5 absolute losses for this prediction. It's hard to get the curvature right here. There we go. Okay? Those are our 5 absolute losses. What about our squared losses? Maybe we'll make this a little smaller. Well, there, just the purple number squared. So 64, 361, 25, 100, and 144. Okay? Here's the key. 80 is the point at which the average of the red numbers is minimized. That we know, we already proved it using calculus. But what I want to give you an intuition for is that it isn't actually the number in this case where the average of the purple numbers is minimized. And let's talk about it. I don't yet know what number minimizes the average of the purples. But I'll tell you that it's not 80. And here's why. What would happen if I moved 80 to 81? well then I would get 1 unit further from those two things. So my absolute distance from the left would go up by 2. I'll get from 19 I go to 20, and from 8 I go to 9. But I'll also get 1 unit closer to all 3 of these things. So instead of 5, 10, and 12, I would have 4, 9, and 11. So my average absolute distance, well, the sum of that at least, goes up by 2, but then down by 3. Which means overall, I'm doing 2 plus 3, which is -1. My average absolute loss goes down by moving to 81. Okay? And so the key idea here is we don't yet know what the best prediction is if your loss function is absolute loss, but it's not necessarily 80. In this case, it's not 80. So in general, it can't be the mean, it's something else. Okay? And I saw that by moving from 80 to 81, my average absolute loss goes down. Okay? I'll try and visualize that here. Has lower average absolute loss. If you had to guess, because 81 has a lower average absolute loss, but then I could repeat that argument again. 82 would be even smaller. 83 would be even smaller. 84 would be even smaller. What do you think the optimal prediction is using absolute loss? Hunter? It's the median. Okay. Well, is it? I don't know. We'll find out. Good guess. The question is, where did I get 361? It is 19 squared. So maybe I'll annotate this. Okay. All right. So what I want to do now is repeat the same 4-step process that I used several slides ago for squared loss, but with absolute loss. Okay? Again, the term average absolute loss and mean absolute error mean the same thing, and so the more common term is mean absolute error, and that's what I'll use from here on out. But notice, it looks the same as mean squared error. All that's different is instead of actual minus predicted squared, it's absolute value of actual minus predicted. And so the question is, what is the new h star? We already know it's not going to be the mean, because the mean of those data points was 80, but we found a different h that had a lower mean absolute error. So there must be some other formula for the best prediction when you're using absolute loss. But what I want to do is find what that new best prediction is. Sound okay? And so to do that, we have to minimize mean absolute error. Okay? And let's try doing that using calculus. You ready? Questions about what we're doing, what the point of it is. Okay, so again, we will follow the same 4-step process where we'd like to minimize mean absolute error, and that involves 4 steps. Taking the derivative of this function, which again only has one variable, h, with respect to h, setting that derivative to 0, solving for the resulting h star, and performing a second derivative test to make sure we found a minimum. Now we don't have all day here, so we're not going to do the second derivative test. We will still do the first 3 steps. And again, the first step will be to find the derivative of the individual loss function. Okay? And so that will be step 0, we'll call it. Now here's where things get tricky. And we alluded to this in the last lecture. The absolute value function, you can't take its derivative using the regular chain rule, power rule, quotient rule, product rule type stuff you learned about in calculus, because it is actually defined piecewise, or think in terms of if statements. Okay? The precise way the absolute value function is defined is if x is positive, return x. If it's negative, well then return negative x, because negative of negative x is a positive number. Okay? There's a third case, which is what if x is 0, return 0, Now, I could have bundled this in with one of the other two cases. Like I could have said, return x if x is greater than or equal to 0, because 0 and negative 0 are the same thing. But you'll see in just a second why I broke this into 3 cases rather than 2. Now, the plot of the absolute value function looks like this. And you'll see there are 3 cases. The first case is where this corner occurs. And that's when h and yi are the same number. Well, when that happens, the absolute value of yi minus h is just the absolute value of 0, which is 0. That is this first case here. Okay? If yi and h are the same number, well then the absolute value of yi minus h is 0. Okay? Then it's just a question of, is h bigger than yi or is it less than yi? Now this plot here, what am I looking at? On its x-axis, I have increasing values of h, and on the y-axis, it's just the output of this function. The corner is when h and yi are equal. Okay? So over here on the right, I have the case where h is to the right of yi. And in that case, the absolute value function is just returning h minus yi with no absolute value. Right? The way to think of it is this. Basically, if h is bigger, well then do h minus yi. But if y is bigger, then do y minus h. Basically, it's just always big minus small so that the output is positive. Do we agree? Okay. That means, well, the case we just discussed is this one, the one where h is bigger than yi, I should say. And then over here, we have the case where h is to the left of yi. But remember, this is yi. So here, h is bigger. Here, h is smaller. Well, if that's what's happening, well then, yi is bigger, so we're going to do yi minus h. Okay? And that is the first case. Okay? So questions with this piecewise definition of the absolute value of yi minus h. Because the next step is finding the derivative of this thing, which will be the derivative of these 3 individual cases separately. Sound okay? But what questions do we have with what's going on here? Random thought, but like a few slides ago, I was just thinking to myself, like, wow, I enjoy this so much more than DSC 10. I don't know, maybe you don't think that way, but I really like this stuff. Not that I don't like DSC 10, but it's just been a while since I taught this. Okay, so like I said, our goal now is to find the derivative of the absolute value of yi minus h. And we're going to use this piecewise definition of this absolute value to help us here. Okay? Now, again, there are 3 cases. The first case was when we are over here. Well, then what the absolute value function is returning is h minus yi. What is the derivative or slope of this line segment with respect to h? Yeah, it's just positive 1. And so in this case, where h is the bigger number, what we're outputting is positive 1. And what about over here? In this line segment, where we're outputting yi minus h, what is the slope there? Good, negative 1. Okay? Now, what about the case where yi and h are the same number? What's the derivative there? It's undefined. Okay, so that's where things get tricky. Oops. Okay, and why is that? Well, without getting too into the calculus-related details, in order for a derivative at a point to be defined, the slope of the tangent coming in from the right needs to be the same as the slope of the tangent coming in from the left. And here, the slope is 1. Here, it's negative 1. There's no gradual transition from negative 1 to 1. Okay? And so the derivative at this point is not defined. If instead there was some sort of smooth transition like this, but then like a smooth version at the bottom, then the derivative would be defined. But that's not how it's working here, and so the derivative is not defined. But fortunately, we can ignore this for now. And it turns out that the rest of the math still works out okay if you just pretend that this case doesn't exist. Okay, and just keep in mind with whatever you do in the future, you can't find the derivative in the case where h is equal to a yi. Okay, but everything else will still work out. Okay? So now we have this. And we'll note that this is why I put derivative in the title in quotes, because it's kind of the derivative, but there's some nuances here. What we're now ready to do is find the derivative of the entire mean absolute error. Okay? And so we can use the same properties from before in pulling out the constant and then distributing the derivative operator like so. So we'll get that this is 1 over n times the sum of these things. Okay? Now here's the key idea. What I've highlighted in blue or overlined in blue could only be one of two possible numbers. What are those two possible numbers? Yeah, it's -1 or +1. Okay? So this entire thing, I guess maybe I should put it like this. This entire thing is a sum of a bunch of +1s and -1s. How many total numbers are we adding? N. Some of them are 1, the rest are all -1. Okay? We're adding whenever the input h is greater than yi, and we subtract 1 whenever h is less than yi. Okay? And so that means I can write this in this kind of strange form. Okay? It's 1 times the number of data points that h is greater than minus the number of data points that h is less than. Okay? Why is it a minus here? Well, it's the number of points that fall into this case times the value for that case, which is -1. Okay? And this is what we call the slope of mean absolute error. And it's an important result I wish there was a podium that was a little taller than this. No, we'll write literally here, important. Not only for helping us figure out the optimal prediction when using absolute loss, but also because it's like a common theme in DSC 4DA homework questions and exam questions, like properties of the slope of mean absolute error. Okay? And so just so we're familiar with what this terminology means, let's just work out an example. Let's suppose we have our data points once again. 61, 72, 85, 90, and 92. Let's arbitrarily select some h to be 79. What is the slope at 79? Well, it's the number of points to the left of 79. That is the number of points that 79 is greater than, which is 2, minus the number of points that 79 is less than, that is the number of points to the right, over 5, which is -1 over 5. Do we agree? So an easy way of thinking of this is number of points to the left minus number of points to the right over number of points. Okay? And so, repeating what we have here, oh, I don't know how that happened. Repeating what we have here, we have the derivative, well, in quotes, so number of points h is greater than, minus number of points h is less than. And what I want to do is set it to 0. Okay? Now, to do that, I'm going to start by multiplying both sides by n to get rid of this constant. And when I do that, and then add this term to both sides, what I get is the number of data points less than h should be equal to the number of data points greater than h. Okay? Taking a step back, what this is saying is the h star that minimizes mean absolute error is the one where the number of points to the left of h equals, and that's this, here, equals this, which is the number of points to the right of h. Okay? Big picture takeaway, a lot of math, but what is the takeaway? We found the derivative of mean absolute error. That was 1 over n times number of points to the left of h minus number of points to the right of h. We set that to 0, rearranged, and the conclusion is that the constant number prediction that minimizes mean absolute error is the one where this statement is true. That is, it's the one where the number of points to the left of my prediction is equal to the number of points to the right of my prediction. Okay? And what does this resemble? A number where there's an equal number to the left and right. Median. Good. So indeed, the median minimizes mean absolute error.